Thank you, Roy. Thank you for that very nice introduction. Let me see, is this the right volume? I think it sounds like it is. It's a great pleasure to be here. I am a professor here. I've been professor for 13 years. This is rapidly turning into one of the best days of a year for me. Last few days, I felt a little bit under the pressure to prepare this talk. And what fun activity it is to talk about one of the really great discoveries of our time in science. So I'm a cosmologist. Cosmologists are essentially astrophysicists who work on the largest scales in the universe. So Big Bang, dark matter, dark energy, early universe, as opposed to individual objects like planets and stars. We study universe as a whole. And I'd like to tell you about one of the great discoveries and mysteries of present time in cosmology, but also just in physics and in science in general, which is dark energy, which is the fact that universe is expanding faster and faster. But I'm going to go back a little bit and consider this picture taken by Hubble Space Telescope. If I ask you what are these, most people will know these are galaxies. Galaxies are the biggest things out there in the universe. They are groups of stars, and each galaxy has maybe 100 billion stars, very large number. You can see a few by eye, but most of the time you have to have a good telescope image in order to see galaxies. Now, what they are didn't used to be so well known. And in fact, exactly 100 years ago, in 1920, there was a so-called great debate in Washington, D.C., at the Museum of Natural Science between two leading astronomers of the day, Curtis and Shapley. And this is the so-called Shapley-Curtis debate. The question was, what is the nature of these so-called spiral nebulae, which we today call galaxies? These things seen on the sky, for example, such as Andromeda. So there's a picture of Andromeda. What is its nature? Shapley thought they are part of our galaxy, the Milky Way. These are just groups of stars within the Milky Way, and all that there is out there is Milky Way and its parts. And Curtis thought that there's evidence that these are the so-called island universes, separate objects, which today we call galaxies. Well, of course, Curtis was right. They are galaxies. They are not part of the Milky Way. But if there were Saturday morning physics talk 100 years ago, this would have been the topic, maybe. What's the nature of of these spiral nebulae? So they are actually much farther away. They are not part of the Milky Way, and we call them galaxies. So today, of course, we know there are many billions of galaxies in the universe. Each one has over 100 billion stars. And they are also billions of light years away. That is what you're seeing today, like this picture is showing them as they were a few billion years ago, because it took light a few billion years to get from them to us. Okay, so that's the nature of galaxies. Now let me go forward a little bit in the year 1929, when American astronomer Edwin Hubble makes one of the great discoveries of all time. He makes the discovery that universe is expanding. Now, Edwin Hubble, he spent time at University of Chicago and at Yerkes Observatory first, which is in southern Wisconsin. And then he went to the world's best telescope at the time, 100-inch, that's to say 2.5-meter, Hooker telescope at Mount Wilson in California. This is close to Los Angeles. Today, there's light pollution. It's not the best place to observe. At the time, it was the world's premier observing site with the best telescope. So what did Hubble do? Well, to talk about expanding universe, let's talk about expanding space of any kind. And let's talk about expanding bread. So say you make a raisin bread. Maybe that's not the most popular kind of thing to make. But let's say you bake raisin bread. So you have bread with raisins inside. That bread is space. The space grows as it's in the oven. And as bread grows, these raisins are moving with the space. And then it turns out that the two raisins that are nearby, they are receding from each other. And two raisins that are far away, they are also receding from each other, but they're receding faster. So the farther they are from each other, the faster they are receding from each other. So I want to point out here, there's nothing mysterious about the universe in this story. This applies to any expanding space, including bread, okay? There's an expansion law for bread. It's a space that's expanding. Well, for the universe, Hubble, he didn't set out to do this, but he discovered. So remember, for bread, the farther away they are, the faster they are receding. So the question is, if you look at galaxies away from us, imagine you are sitting at one of the raisins and you're looking at other raisins, and other raisins are galaxies, is it true that the farther away they are, the faster they are receding, they are going away from us? So he set out to measure this relation. To measure this, you need to measure two things. You need to measure distance to other galaxies, and you need to measure their speed or velocity. It turns out velocity is easy and distance is hard. So in the next few slides, I will explain a little bit how you measure velocity and then how you measure distance. Well, measurement of velocity is the easier part. And here it effectively is equivalent to what we call Doppler effect. It's a fancy name for absolutely everyday, not quite everyday, but common experience to all of us, which is that if you hear an ambulance car in the street, or any vehicle that's producing a sound, you hear a higher pitch as it's approaching to you, and you hear a lower pitch as it passes by you. So you hear that, right? You hear that, everyone, you can hear it just even from cars. And the reason is, as it's approaching you, the sound it's emitting, it tends to be bunched up here because it's moving. So you hear a higher pitch. As it's receding away from you, here you're behind it, the sound, it's carrying the sound with it. So you're hearing waves that are more separated. Really, for this to happen, the speed of the ambulance car has to be not that much smaller than the speed of sound. And speed of sound, as you know, isn't that great. It's not like the speed of light. So this happens, and that's why you hear it. So I'm going to demonstrate here the Doppler effect just to tell you what I'm talking about. This is going to be a little bit loud. Apologies for that. Maybe I'll shut off my microphone. And I will whirl this above my head. It's going to be producing squeaky sound, and let's see what we hear. Bit painful to listen to, but you heard it, higher and lower pitch. I didn't do it too fast, but you heard the effect. So this is called the Doppler effect, and it has to do, so by measuring the pitch, for example, you could measure how fast the ambulance is moving. So that same effect for sound applies for light. It's the same as the Doppler effect, and if some galaxy, let's say you observe light, some spectral lines from some galaxy or star, it doesn't matter. If it's receding away from you, if it's going away from you, the light you see would be shifted to longer wavelength, that is to say lower frequency. So this is like an ambulance car going away from you, you hear lower frequency. That's called redshift. It's shift to the red if you think about blue to red spectrum. If it's coming to you, then it'd be blue shifted. Then you'd hear a higher pitch and you'd hear a lower frequency, lower wavelength, right? So you can measure, even now it's compared to the speed of light. Speed of light is great, but galaxies are also much faster than the ambulance car moving through space. So the question is, what is then the speed of galaxies relative to us? And you might guess half of them are receding away from us, half of them are coming toward us. Not true. Almost all of them are receding away from us. All the galaxies are running away from us. One notable exception is Andromeda that I mentioned already. Now Andromeda is coming to us. There's no more going back. Andromeda is gravitationally attracted to Milky Way, and Milky Way and Andromeda are going to collide very soon, in a few billion years. That's very soon in cosmology. They're going to collide. That's too late for Andromeda to escape, but every other galaxy basically is going away from us. Is it because we are special somehow? No, it is because space is expanding. So that was remember velocity part, the easy part. Now remember that graph, I had velocity and distance. Distance was hard. Now, distance is the famous hard thing to measure in astronomy, and you can imagine that's the case. You see something on the sky, maybe it's some star or galaxy, it has a shape, has color, but how far away is it? It's really, really hard to know. So you want a kind of object that you would almost wish it has a written distance on it, so you can read it off. Well, you don't get that, but you get special kinds of objects like stars that have certain properties, and these stars are called Cepheid stars. It's a kind of star. Now, you may ask, why are we talking about stars now? We talked about galaxies. Well, these stars that live in galaxies are special. They pulsate. They light, brighter, dimmer of a period of a few days. But they pulsate so that people found an empirical law, that is to say, it just happens, that the longer the period is, the bigger the luminosity, that is, the more light they put out. So the ones that have long period, take more days to go bright and dim, they are intrinsically more luminous, they're putting out more light. And then the ones that are faster, shorter period, they intrinsically have less light, less luminosity. Think about it, their power. This is the luminosity is like their power, the power they put out. Now, this is the only equation I'm going to show today, but I'm going to show it a couple of times. It's a relation between flux, the amount of light you measure from an object, luminosity, which is the thing I just mentioned, the intrinsic amount of power object puts out, and distance. And this is clear. For example, sun has some luminosity, so given our distance from the sun, you can tell how much light do you feel, right? This is the thing you measure if you lie down on the beach anywhere. So likewise, from Cepheid or some object, you can measure the amount of light. You would love to know the distance. And this is the sticking point. How much intrinsic energy is it putting out per second? And that luminosity now you can get from the period, because you can use this period luminosity relation, measure the period, infer the luminosity, plug it in here, measure F, and get the distance. So this is a way to get distance. So this is the hard part in the relation Hubble needed to get distances. So Hubble did all that, and here's the actual real plot from Hubble's paper. It's not a pretty looking plot, because this is a real paper from 1929, but it shows distance on the x-axis, the thing you get from Cepheids, and et cetera, and velocity, the thing you get from Doppler shift, basically. You see a huge scatter of points. Points are all over the place here. There's looks like a bunch of garbage, basically. It looks like all over the place. And now Hubble had, almost as if somebody whispered in his ear, he put a line through it. Almost like somebody said, hey, put a line through it. Okay, just trust me, it's a line. So Hubble put a line through it and made one of the great discoveries of all time. Because remember, line is prediction of expanding space. The farther away you are, the faster you're receding. Now, one incredible thing about this plot is it is a line. And the universe is expanding. But the slope of the line is the expansion rate. It's how much faster are you receding per distance. It's called the Hubble constant, so how many kilometers per second. Megaparsecs is like 1,000,000 light years. It's a unit of distance. So every megaparsec, farther you are away, you are receding in our universe 70 kilometers per second more. For example, galaxy that's 1 megaparsec away is receding 70 kilometers per second from us. One that's 2 megaparsecs away is receding 140 kilometers per second from us, and so on. Now, one incredible thing is that Hubble got the relation right, but he got this slope way off. Hubble got 500 for this number. So he was way, 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 way off on the Hubble constant, even though he discovered the law. And it took decades for us to converge to this value. Now, this will become a very important just near my talk. So remember this, Hubble constant is ballpark 70 kilometers per second for each megaparsec. So this was the discovery of the expanding universe in 1929. It's really one of the great discoveries. The universe is expanding. Why is it expanding? Into what is expanding? I didn't say that yet. Hubble didn't know that. The fact is that things are receding away from us, and in fact, they are receding from every other object. So I have a couple of demos here to demonstrate. In expanding universe, I'm going to have expanding, a square on the wall. And as the square, as this space, being this board, this pattern on the wall is expanding, every point is expanding from every other point. So not only does the bright point in the middle recede away from its neighboring, but if you take any 2 points, they are becoming farther and farther away from each other. Because that's a very basic demo. A little bit more sophisticated demo, just a little bit, is given by this balloon. So I'm going to blow up this balloon here. This is going to be my universe, so to speak. I'm going to turn it on. Have it like that. And we'll give it a few moments. And as it starts to expand or not. Oh, I see. It was already on. Thank you. So we're going to start expanding this universe. There are some galaxies on it. Actually, they look like stars, but there are galaxies on it. So galaxies in this universe, and it's expanding. So what happens is that it gets bigger and bigger and bigger, and I'll leave it here for a while. Every galaxy is receding from every other galaxy. If you pick any one of them, none of them is special, it's receding. And the farther away its neighbor is, the faster it's receding. Okay, so one nearby is receding at some speed, one far away is receding faster. So this is a pretty good model of expanding space. There are some limitations to this model. One limitation is that this is, of course, two-dimensional. We live in three-dimensional space. This is two-dimensional. Another limitation is that each galaxy seems to be growing. In real life, galaxies themselves are not expanding with the universe. Just like this room is not stretching with the universe, nor is this table. You really need two separate galaxies to be receding away from each other. But the biggest limitation of this model is that this universe here, this surface, is expanding into something. I'm here very comfortable in three-dimensional space, and I'm looking at this 2D space expand into the space I live in. For the real universe is not expanding into anything. It's all there is. So it's just growing, but people often ask, into what? There is no fourth dimension into which it's expanding. That's it. It's a little bit hard for our minds to come around that because we are used to space expanding into another space. Like we are looking at this, and this is still within our 3D. But But the real universe is not expanding into anything. It is all there is. So that's a good model of expanding space, demonstrating yet another Hubble law. So there's a Hubble law for this balloon. There's Hubble law for the expanding universe. OK, so having talked about this discovery of the expanding universe, let me now briefly go through the history of the universe, kind of maybe step back, and this will include some other discoveries we in cosmology have made over the past 100 years. So this is a time axis. This is a Big Bang. This is the present day. Time is running down. And this is a very rough chart. You know, space is getting bigger, as you see. And I'm just going to review it quickly from time equal to 0, from the Big Bang to 13.8 billion years after the Big Bang, which is today. So Big Bang is time equal to 0. That's when we start counting. Expansion starts. Did it happen here? Did it happen there? It happened everywhere. Okay? It happened everywhere. Details are really not very well known. People talk about it, but there's no way to probe t equal to 0. That time of the Big Bang itself is currently beyond reach of any probe. And don't ask, please, what happened before the Big Bang? We don't know. Time started at the Big Bang, we think. What does it even mean? We're not sure. Was there time before? It's actually possible. There are some speculations how there could have been, this could be a baby universe out of other universes. That speculation exists. We just don't we hope to have a way to probe this in the near future, but not just yet. However, one of the great triumphs of cosmology is that we know something about incredibly tiny moments after the Big Bang. At about 0.0000301 seconds after the Big Bang. So unimaginably, so trillionth of a something, whatever, seconds after the Big Bang. And these are high energies and exotic, potentially new physics, but we particularly know that something called inflation happened during that time. This is not increase in prices of products. This is a rapid increase of the size of the universe. Now, inflation would be a great subject for another Saturday morning physics talk. It's a fascinating topic, and it's been confirmed by data by and large, but I won't have a chance to talk about it today. Then about less than a second after the Big Bang, we have a quark soup of particles called quarks. They have funny names like up and down and charm and strange, and they make up protons and neutrons that we are very familiar with. But this was very early time. And in fact, only about a minute after the Big Bang did nuclei form. Now, nuclei are elements like hydrogen and helium. So they formed, so these quarks finally had mercy to combine together, and then protons and neutrons combine into nuclei only about a minute. And this process is very well understood in cosmology, very, very well understood for about 50 years. Hydrogen and helium and lightest elements formed then, and heavier elements like iron formed in stars much later. About 300,000 years, so this is not going second by second, obviously. This is jumping a little bit. 300,000 years, something called cosmic microwave background was generated. The CMB is the radiation left over from the Big Bang. It's the photons, the light left from the Big Bang. Well, what happened to that light before 300,000 years? It was there, but it was bouncing off of other particles. So if you imagine particles of light, they were bouncing like a like a ping pong. And then finally, they were able to not bounce anymore. The universe rarefied enough, they were able to go. And that microwave background we observe today. So one of the great discoveries in cosmology now in the 1960s, a long time ago, was two engineers, Penzias and Wilson. They were Bell Labs engineers. And for the younger in the audience, Bell Labs at the time was like Google today. It was a dominant company. It was absolutely dominant company with most brilliant people, engineers and others working for it. So they were Bell Labs engineers, and they had an antenna in Crawford Hill, New Jersey. So this is an American discovery. And they found strange noise. What is this noise coming from? It's messing things up. It turns out the noise was this radiation, faint radiation from the early universe. I drew a picture here. It's not a literal picture, but it's uniform radiation. It's the same thing in all directions in space. It's about, you can quote its effective temperature, 3 Kelvin, about that at 0. So it's like very low energy radiation. You're not going to get suntan out of it. Very low energy, barely discovered with this huge antenna in the 1960s. They won Nobel Prize. Then another Nobel Prize was discovered for another great discovery. That radiation actually isn't perfectly uniform. And there are fluctuations, we call them anisotropies, of about 1 part in 100,000. So 1 part in 100,000 is like going to a deep ocean that's a kilometer deep and seeing waves that are, I think, a centimeter high, like half an inch high, right? So it's a small fluctuations, but non-zero. So this map, it's a real actual map of the sky. This is old sky, and you can see these fluctuations. We subtracted the temperature, and then we're just looking like fluctuations. So here I have another map. This is a beach ball. It's a very nice beach ball. It's actual map of the CMB. It's the same as that map, similar. It just has this extra red thing around. That's a galactic kind of dust noise that's in the way. But imagine you're sitting in the middle. So you're sitting anywhere on Earth, and you're observing the sky. So this is like the sky. If you were sitting in the middle of this ball and looking out, you would see the sky, and you'd see 3 Kelvin, but slightly hotter, slightly colder, slightly hotter, slightly colder. And that's that same. If you unroll that map of the sky, that's the one you see on the screen. So this is also called the Rosetta Stone of cosmology by some people, because by measuring the statistical distribution of these hot and cold spots using sophisticated statistical techniques, lots of math, lots of theory that was developed over decades, you can discover wonderful things. Now, some of you may have heard of Rosetta Stone, this basalt stone dug up by Napoleon groups in Egypt, where they were able to read 3 scripts and decipher hieroglyphic script using this one piece of stone that's now in the British Museum in London. There's one incredible piece that can tell you wonderful things. We in cosmology feel like the microwave background is like that. It's one map that tells us many things. Among other things, when we say universe is 14 billion years old, that information comes from this map. The structure of hot and cold spots, the statistical distribution is sensitive to that. Another thing that this measures is the Hubble constant expansion rate. And I'm going to come back to that in a little bit. Okay, but anyway, this is a CMB. It's been released 300,000 years after the Big Bang. We observe it today. It's some radiation from the early universe. Moving on, we enter the Dark Ages. Now let's see, in Europe, Dark Ages were 12, 13, 1400s. Poor times, dark, lots of disease and dying and unhappiness, not much going on. Likewise for the universe, the Dark Ages, dark and cold and not much going on. But eventually, during these after the Dark Ages, first stars start to form. Stars and then galaxies. And then, of course, the present-day universe we are pretty well familiar with. There are stars and galaxies everywhere. There's dark matter, which I won't have a chance to talk about much, but it's a certain kind of matter that is dark, that people are trying to find. And then there's a big surprise in the store called dark energy. That's the subject of this talk. Now, I'm going to run, this is not like a movie, this is a simulation. So this is going to run for a couple of minutes. I'm going to talk during this. This is starting at the Big Bang, and it's showing you billions of years after the Big Bang. It's a numerical simulation on the computer, so it's not like a movie people would make for a film on television, right, where somebody makes up some fancy graphics. At each step here, there are equations. Let me just try to get rid of, well, sorry, let me run it again. Okay, so At each step in this movie, there are physical equations that are being solved. And so this is there are billions of particles that are being moved by the laws of physics in this simulation. This simulation takes millions of CPU hours. You run it on a supercomputer. It takes several months to just produce one of these simulations. So it's a really incredible effort by cosmologists. And so all the things you see in them are real to the extent that we understand physics. So what you're seeing here is formation of structure in the universe. The camera, so to speak, is also panning around. As you see, it's kind of zooming around this box, and it's also zooming in. It's also zooming in slowly, so you're going to see more and more detail. This is not the whole universe. This is only a chunk of it. But what you see, the bluish stuff you see, is by and large dark matter. And then the explosions and reddish things you see are mostly normal matter, like hydrogen, helium, carbon, and other elements. And you can even see some supernova explosions. There are black holes maybe even that are hiding somewhere in these regions. Now we've zoomed in quite a bit, so we are looking at really a small chunk of the universe. But you see one defining fact of the universe we live in is a filamentary structure, like this, looks like a sponge, right, the structure. That's the kind of thing. Why is there such structure? Because gravity does it, right? So if you just ask the law of gravity, you apply Newton's law of gravity basically to particles, you'll get this filamentary structure. You'll see the filamentary structure in a few moments when the color of this changes, because it's showing both gas and dark matter particles. But now we are, let's see, 9 billion years after the Big Bang, so we are past the dark ages, I think, and into the modern era. It's going to run up until 14 billion years. And now it's zoomed in quite a bit, so you're not really seeing those filaments as much anymore, but you're seeing individual structures. And these greenish, reddish things may be galaxies. Actually, they may be dark matter clumps that surround galaxies. Real galaxies you'll also see. You can actually now, in this contrast, you can see, so the reddish things and yellowish in the middle, they're galaxies, and then the bluish haze is the dark matter that concentrated. So I didn't talk about dark matter. It's some kind of particle that isn't in the periodic table, that's out there and dominates all of the other matter. And so this is illustrative simulation. It's state-of-the-art numerical. We call it n-body because there are n bodies where n is very large. Simulation that's being done by cosmologists. Well, okay, so that's how the universe looks today. Now, question is, what kind of space does mathematics allow that we live in? Well, space in mathematics, as well as in real life, can be three kinds. It can be flat, zero curvature, positively curved, and negatively curved. Flat space is the most familiar kind. If you have a triangle, angles add to 180 degrees, and two lines that are parallel continue to be parallel forever. Positively curved space is where you have a triangle, angles add to more than 180 degrees, and two parallel lines converge. Now, everybody is actually familiar with curved space. Surface of the Earth is curved. And so you know that there are some slightly strange things that happen. For example, if you walk in a straight line for a long, long time, or fly an airplane for a long time, you'll come back where you came from, right? You may come back to an Arbor if you go around the poles. Because in curved space, you know, in flat space, you never come back if you go in a straight line. But in curved space, you do. You also can do in curved space, follow the straight line 3 times, go along the equator, go to the North Pole, come back to the equator, and you kind of enclose a funny triangle. So geometry is a little funny in curved space. We also know when airplanes fly from here to Europe, trajectory you follow may not be the one you imagine. It kind of looks a little weird, right, to do the shortest. So we are familiar with closed space, with positively curved. We are not so familiar with negatively curved because surface of the Earth or anything we know about isn't negatively curved, but it's a surface of the saddle where angles in a triangle add up to less than 180 degrees. Well, the first person to seriously set out to ask, okay, so what is our universe, our world? Is it flat, positively curved, negatively curved? We don't know it's flat for a fact. It was Carl Friedrich Gauss, German mathematician. He actually climbed peaks in Bavaria, 3 peaks, and from each peak he measured the angle to the other 2 peaks and measured the angle. So he summed the 3 angles and he tried to see if they add to 180 degrees. I think he found they do, but he never had a chance to find this. Because to ask it for a universe, you have to climb to each galaxy and look at the angle to 2 galaxies. You have to go much further than peaks in Bavaria. So of course you can go to another galaxy and ask that question. But it turns out that cosmology that you can measure that same relation I talked about earlier, where, remember, distance on the one axis and velocity or redshift on the other, except before I had distance here and velocity there, now I flipped the axes. And remember, we talked about the slope of this line, the fact that it's a line. This is the relation I talked about before, the linear relation between distance and velocity or redshift. Well, it turns out if you continue those curves, you just have to trust me on this. I haven't really motivated it, I haven't explained it, that you get a different behavior between distance and, say, velocity or redshift, whether geometry of space is flat, open and closed, that is to say, negatively curved or positively curved. So if you just go out and measure, do the same thing as Hubble did, but do it at a larger distance, then you can select between these three curves. And to do that, you use that same relation I talked about before, but now the Cepheid stars are too far away, so you need a new object, and this kind of object is called type 1a supernova. It's an exploding star. It's a case of white dwarf accreting matter from a companion, undergoing explosions. And you know, what does type 1a mean? It's a certain type. Not every type of supernova works. There's a certain type that works. Don't worry why. They're very bright, and when these explosions happen, here's a galaxy far away. Remember, it has 100 billion stars, and one of those stars that exploded is actually comparable to the whole galaxy. It's that bright. It's a tremendous explosion. If it happened in our galaxy, it would be a disaster. But it happens in other galaxies, not very often, and it is bright, but it has a special property that the luminosity is almost the same every time it happens. Now remember, this is the same similar for Cepheid. It's a so-called standard candle. It's a thing you can trust to know how much light it put out. It only works for these objects. For type 2 supernovae, it doesn't work. For other kind of explosions, it doesn't work. It's a similar luminosity only for these special objects. So here's an example. You can see light going up and down, and the supernova happened here. I'm going to run this movie again. This is real data. So here's a galaxy. The supernova is going to be right here. Take another look. It goes up, and it goes down. That takes about a month. So it happens over about 1 month. So if you find such objects, you can measure you know what their luminosity is. Because remember, I go back to the same equation. You can measure the amount of light, and you know the intrinsic amount of light, the luminosity. This is the standard candle. That's the golden information you get. You can measure light easily through your telescope. You'd like to know the distance, but the key part is that you get L. I can make an analogy with cars. Imagine you have a car at night. It's pitch black, you just see lights. Is it Fiat Uno nearby, or is it a truck far away? You don't know. You just see like this light here. I see a light, but you know, I see some of you, so I have a scale of what's happening. If it was pitch black, I just saw that light. I wouldn't know if it's a really bright light far away or dim light nearby. But if I have additional information, hey, this is a light that outputs this much power, then immediately, like, hey, this is a standard car light. Then immediately my brain can calculate how far away it is, right? So that's the key information about what we call luminosity, what in real life we could call the intrinsic amount of light at some car, right? So your brain already does this. It sees lights in pitch black. As soon as you know it's some kind of regular car, it calculates the distance. And you can do the same thing. So with this information now, this is saying the same thing. So you measure flux, you can get distance to the supernova, and then remember redshift you can get also. So now it turns out, okay, great, I just need some supernovae and I can measure that relation, I can find geometry of space. Problem is if you write a proposal to NASA and say, hey, NASA, please, I would like to use Hubble Space Telescope to do this. It turns out it takes about 500 years on average for one supernova to go off in a galaxy. So if you wrote a proposal to say, I'm going to wait 500 years with Hubble Space Telescope and wait for supernova to go off one, that wouldn't go so well. So a key challenge for the cosmology community was to develop techniques to get enough supernovae in half a year, not in a million years. And this was dirty, hard work made by two groups of cosmologists, international collaborations, to manage to observe enough galaxies to be able to guarantee that you will be getting enough supernovae. And those people, in fact, won Nobel Prize in 2011 for the discovery that I'm going to talk about in a moment. These two folks, Rees and Schmidt, were part of one team, Perlmutter of another. And I would say, in my personal biased opinion, even among the Nobel Prizes, this was a big one. This was a really big one, because this was discovery for all time that our universe is doing something weird. But what did they find? Well, they plotted the same kind of thing. This is kind of a distance, except I took a log now, and this is a kind of velocity. The same kind of graph. I'm using slightly different scaling here, so it's not a line anymore. But remember, they set out to see if universe is open, flat, or closed. Remember, now they're going much farther. Edwin Hubble looked right here, really nearby. And now they're looking way out, billions of light years away. And it turns out that neither one of these cases, neither open, nor flat, nor closed, fits the data. This is real data that I massaged a little bit to put it in the form that they're easily visible. In fact, their data favored another model that is the universe that's not made up only on matter, but it's a universe that decided to speed up its expansion today. So matter-only universe never speeds up, but this is expansion that very recently in cosmological terms start to speed up. You can see that the data don't like either one of these three curves. So this new thing, we don't know what it is. We call it dark energy. It was named by my PhD advisor at University of Chicago, Michael Turner. Universe is dominated something but other than dark matter. This new component is dark energy. It makes the universe expand faster and faster. That component is smooth, and we don't know all that much. Now, in the early days, people said, hey, you guys, I know the two teams agreed, but you made some kind of error. Please go back and check. Oh, you forgot about this in your analysis. Not only have many teams rechecked these results, but completely independent methods, unrelated to supernovae or anything like not even distances, have done separate measurements in cosmology and found that there's dark energy. Now, it's amusing. I was asked by a magazine recently to comment on a paper that brings some of this into question, but it's incorrect in my view. And I was quoted by saying, I bet my life the dark energy is there. And then I was thinking later, betting your life on anything is not maybe the greatest idea. Just out of principle, don't bet your life, bet your house or something. But we are that sure that something's going on. Now, what is dark energy, we don't know, but that none of those regular models will matter only. They just don't fit the data at all. We are completely sure of it now. And here's just a very crude movie showing galaxies expanding. And now, check it out. Just now, they start to expand faster and faster. So they were slowing. And then recently, in cosmological terms, that's to say a few billion years ago, they start to expand faster. So that's a very crude movie. This is not a real simulation, but it's showing you the kind of thing that dark energy does. This very unusual, out of the blue acceleration of galaxies running away from each other faster and faster at late times. So now remember, dark matter is not equal to dark energy. This is one of the common confusions because they have similar names. They're totally different. Dark matter, this is a very crude picture. Anytime you see a galaxy, imagine a bluish halo of dark matter. We've seen some of them in a simulation I ran. Dark energy, in contrast, doesn't clump. It's perfectly smooth. And it doesn't act gravitationally. It actually pushes away. It doesn't attract. So it's doing all the opposite things of dark matter. The only similar thing is the name. So here are some basic facts about dark energy. It's smooth. It pushes things apart. Now, it has funny property that its density is constant. So if as the universe grows, you double the volume, you double the energy. Now, if you imagine regular matter, if I have 20 particles in a box, if I increase that box, so that's my universe that grew, the density goes down because the density, I have 20 per volume, and volume went up, so the density of energy of number is lower. Here, the density is constant approximately, so that the total energy in the universe, because the volume grows, increases. And this is actually allowed by the laws of physics. So total energy increases. You can do that in physics, contrary to maybe some basic intuition. So that's what dark energy does. And actually verifying whether it's exactly true that this doubles, or is it exactly doubling, or some other law is at the forefront of research, exactly what the behavior is with time. Dark energy is noticeable only at recent times. If you go back to the early universe, We think it goes away. We don't see any evidence for it. It slows down the growth of structure. And maybe most importantly, the universe is apparently more complicated than needed to be. This is a bit of a philosophical point. You and I could have this very nice conversation, exact same Saturday morning physics and the rest of our lives without dark energy. Because we barely discovered it, right? It's kind of hard to find. So why is it there? Is there a method to the madness? We don't know. What principle is ruling it? But there are lots of ideas for dark energy, and some of them involve things like theoretical predictions. For example, in quantum mechanics, particles pop in and out of air. And this is kind of a more technical thing. I'm only describing it here in a slide. Turns out that this popping up in particles, which has been known for many years, this is allowed, it creates something like dark energy. So you may say, okay, known physical principle can create the effect. The only problem is if you calculate, you find that the amount you predict is unimaginably larger than what you observe. So this is probably the biggest discrepancy I think any of you have seen ever between what you predict and what you observe. It's number of 10 to the 120. Now remember, there are, 10 billion people on Earth, that's 10 to the 10. How many particles are there in the universe? That's 10 to the 80. This is 10 to the 120. So it's completely unimaginably off, this prediction. So this has created a great mystery in physics of why this one model that could work is obviously wrong. It's way off. So this is really putting a lot of interest into studying what's going on with theoretical prediction for dark energy. The other mystery of dark energy is if you look at the time, and if you look at how matter, as the universe grows, time is running to the right, matter dilutes. Dark energy, remember, density is constant. So dark energy was subdominant in the past. It will be dominant in the future. Blue is greater than red in the future. And we just happen to live in an era when dark energy is about 70% and the regular matter is about 30%. It's about 3 to 1 is about ballpark equal. It's not 1 to billion or billion to 1. It's like 1 to 1. So here's another picture. We live in an era. Here's us today. Pie chart is 70% dark energy. The red part is dark matter. The yellow part is periodic table of elements. If you look in the future, it's going to be all dark energy. If you look in the past, it was all different kinds of matter. So why are we just born? It's like you wake up someday and you find something special. 3 birds are chirping at the same time at your window or something. Some kind of unusual situation you ask yourself is. So this may or may not be a coincidence, but it's something that cosmologists are working on. Okay, so I mentioned 2 big conundrums, the prediction and why. So what is dark energy? Well, we don't know. Obviously, this is one of the great mysteries of cosmology today. Is it vacuum energy? Well, the prediction is way off. Is it modifications of Einstein's theory of relativity? Maybe. A lot of people are working on that. Is it some kind of funny fluid that fills the universe? Maybe. Or most likely, it's something else. Well, what, of course, would be a wonderful thing to find out. There are some consequences of dark energy that are really kind of bizarre. One of them is a sure thing. In the accelerating universe, galaxies are leaving what we call horizon. So imagine some galaxy far away. We see it because its light can get to us, but now it's accelerating from us, and because it's far away, it's accelerating a lot. And like a few billion years in the future, we're not going to be able to see it because it'll be so far away that even light won't be able to get to us. It'll be receding at such a rate. So in fact, in 100 billion years or so, the sky will be empty, except for Andromeda. That's going to hit us in a few billion years. But after that, Andromeda and we will settle, and much, much future generations, 100 billion years from now. This is a sure thing, by the way, if dark energy is doing what we think it's doing. And the thing that's even more bizarre, that's not a sure thing, because under certain circumstances, which we are not sure if they are satisfied or not, the dark energy is creating so much acceleration that the houses and the planets and the houses and smaller things, and moments later, a fabric of space will rip itself apart in a called Big Rip. And for those of you who are studying some math, I can say this is where the size of the universe becomes infinite. The distances become infinite in finite time. So not in infinite time, in finite time, they become infinite. I don't even understand what this means intuitively, but equations show it. we don't know whether these conditions are satisfied. So this is a maybe, depending on certain conditions, which we are still trying to measure. This here is a sure thing, okay? So these are some bizarre, big rip is a maybe, and things leaving. So where are we? We have a worldwide effort. This is, again, this beach ball, and we are in the middle of the beach ball, and I'm showing some galaxies that we measured, We are sitting at the center. This is kind of the observable universe. There are some galaxies. The first survey was smaller than this red triangle in 1980. It's called Harvard CFA survey. And then as you look at the newer experiments, dark energy survey, something called DESI, LSST, Euclid and W first, and even new methods, which I won't have a chance to explain, they will explore bigger and bigger chunk of the space we live in to find out what dark energy is. So if you look at the biggest telescopes built for cosmology, many of them have dark energy, or letters D, E in their title. That's really the #1 motivation, at least as far as cosmology is concerned, is to find out what dark energy is. And in my personal and possibly biased opinion, in all of astronomy and astrophysics, the only thing in my mind that comes close to how at least I'm excited about it is extrasolar planets. So extrasolar planets are very cool, finding these planets around other stars, and this dark energy is right up there with it to try to understand what's our universe doing, why is it speeding up the expansion. So the idea is to measure galaxies and supernovae and measure a lot of different things better in order to find out what's going on. That's the idea, and that's what we work on. Now, one of these surveys is dark energy survey. I and Dave Gerdes, our chairman, and many of us in Michigan are involved in it. It's on Cerro Blanco telescope on a peak called Cerro Tololo in Chile. And it's in Chile. It's a sky survey. It's this big building. 700 scientists worldwide. We are working on the analysis now. Observations are actually finished, but we are working on the analysis. And I have a few pictures. I'm a theorist, so I'd never gone observing in my life up until like a year ago when I went to Chile to observe. And here I'm sitting in front of 8 screens. I'm pretending I know what I'm doing. I actually had no idea what I'm doing. But everything was automated, so it was very nice and very civilized. So I was a complete outsider to observation, and I came away very impressed. I can tell you it's a beautiful site, completely quiet, gorgeous site. It's a huge building. This door is the size of a very large truck. So this is like a 7-story or 10-story building. It's a huge building. The size of a person is much smaller. You climb there. You have this big telescope with fancy instrumentation and very nice software. In fact, by the time I was there, you can set software to observe, and you can read the book the rest of the night. It's just automated. It's almost like artificial intelligence. I was completely blown away. But these are the kind of observations we are doing to try to find out what dark energy is. Now, that's basically that's my main story, okay? Now I have some breaking news cycle. Breaking news is news that happened in the last couple of years, and this is the latest and greatest excitement. What are we excited about today, this year in cosmology? It's something called Hubble tension. What kind of tension is it? Well, there are two kinds of measurements of the Hubble constant. This method I talked about from type 1a supernovae and Cepheids, remember, you do the same as Hubble did. You measure Hubble constant, same as Hubble did. You get 74 kilometers per second per megaparsecs. Remember, the structure of the hot and cold spots also tells you this expansion rate of the universe. You get 67. Now, you may say, well, excellent. You told us it's about 70. One number is 74. The other number is 67. Perfect. Except, take a look at the error bars. This is plus minus 1.4. This is plus minus 0.4. These are the margins of error, right? This is you report the error. The errors are very small. The CMB error is tiny, and the first error is still small. So in fact, if you look at the difference, which is 74 minus 67 is 7, even in units of the loss of this larger error bars, it's 5. 5 margins of errors, because it's 5 times 1.4 is the difference between these two numbers. So in cosmology and statistics, we call this 5 sigma. 5 margins of error. 5 sigma, any physicist will tell you, is it's a threshold for excitement. For real excitement, something doesn't fit. Because formally, it corresponds to 99.99997% confidence that these two numbers don't match. Now, of course, you may say, look, come on, you messed up. This was really a bigger error bar, but you forgot to include something. Multiple teams around the world have redone the analysis, have looked at this, have checked and rechecked. There was, I think last year, there was something like 10 conferences devoted to this. So many people have looked at this and kind of agree that's about right. And this is why we are excited, not just because one person went out and is claiming something. So in my personal opinion, this is the cutting edge kind of development, is this discrepancy that won't go away. These two numbers should be the same unless if something in our assumptions is wrong. And what in our assumptions could be wrong? Well, new physics, new behavior, dark matter and dark energy, they won't go away. But is it new behavior of dark energy? Is it some kind of new, is it not negligible at early times in the universe? Some other new effect that we haven't thought of. So many people are working on this, writing papers about this. This is the kind of cutting edge. I don't have a resolution to this. This is the current excitement. But the exciting thing about it is a very solid, two very, very solid measurements. These are not just two random. They don't agree to a margin, and the difference is such that it's what we call 5 sigma. Okay, so that's the latest from the cosmology front going on around the world, is this Hubble tension. And there are many conferences and workshops right now being devoted. In conclusion, I said that universe is expanding. It was smaller in the past. It started with the Big Bang. Dark energy is for sure there. I'm guaranteeing it with my life, apparently. And universe is accelerating. And there's a worldwide effort to understand why. And I talked about Hubble tension, which is discrepancy in modern measurements of H0 by two trusted methods and teams that may indicate a new effect or a new major discovery. Thank you.